On your screen, there's a big wave. There are also people who make noise in the morning. And here's a glow stick that you played with during your childhood. Now, what do you think is the similarity of the three? They are all manifestations of the same thing. And what's that thing? Let's know about it in this lesson. Hello class, I am Kerby Tacorda, a BS Mathematics and Science teaching student from the University of the Philippines, and I am one of your science teachers here in the Filipino Science Hub. In this lesson, we are going to talk about the differences between a mechanical wave and an electromagnetic wave, and the differences between transverse waves and longitudinal waves. I hope that we're ready to learn the science of waves, feel the waves while seated, and enjoy the science behind. If we are ready, let's first have our learning objectives so that we won't get lost along our way in this learning. After this lesson, the student should be able to relate the frequency of a wave to its wavelength, differentiate mechanical from electromagnetic waves, and differentiate transverse from longitudinal waves. Before we start, let's take a look at a pretest I prepared for you. You can take a screenshot of it or you can write it on a sheet of paper. You can also try to guess the answer, and at the end of the video, we will see if your answers were correct, right? You do not have to worry about your wrong answers for now because it would serve as an overview of what you're going to learn from this lesson. Alright? Number 1. What do you call the number of waves that pass a point in a given amount of time? A. Amplitude. B. Wavelength. C. Frequency. And D. Hertz. Number 2. Which of the following shows the correct relationship? Letter A. Frequency is directly proportional to wavelength. Letter B. Frequency is inversely proportional to wavelength. Letter C. Frequency is neither directly nor inversely proportional to wavelength. And letter D. Frequency is only related to amplitude. Number 3. Which of the following is not an example of a medium through which mechanical waves can propagate? Letter A. A narrow log. Letter B. Cooking oil. Letter C. A perfect vacuum. And letter D. Helium. Number 4. Which of the following does not describe mechanical waves? Letter A. Noise coming from your neighbor. Letter B. A phone vibrating when there is a notification. Letter C. Light coming from distant stars. And letter D. Waves created by a jumping rope being used by children. Number 5. It's a true or false question or statement. Electromagnetic waves cannot travel without the presence of matter through which it propagates. Again, electromagnetic waves cannot travel without the presence of matter through which it propagates. Number 6. True or false? The light that enables us to see things travels as transverse waves. Again, the light that enables us to see things travels as transverse waves. Number 7. Fill in the blank. In longitudinal waves, the direction of the particle motion is blank to the direction of the energy of the wave. Is it parallel, perpendicular, angled obtusely, or angled acutely? Again, in longitudinal waves, the direction of the particle motion is blank to the direction of the energy of the wave. Letter A. Parallel. Letter B. Perpendicular. Letter C. Angled obtusely. And letter D. Angled acutely. Number 8. Fill in the blank. In transverse waves, the direction of the particle motion is blank to the direction of the energy of the wave. Is it parallel, perpendicular, angled obtusely, or angled acutely? Again, in transverse waves, the direction of the particle motion is blank to the direction of the energy of the wave. Letter A. Parallel. Letter B. Perpendicular. Letter C. Angled obtusely. And letter D. Angled acutely. Number 9. You just need to look at the figure. What is the red point or the red arrow pointing at? Is it A, compression, B, reflection, C, refraction, and D, rarefaction? Again, what is the red arrow pointing at? A, compression, B, reflection, C, refraction, and D, rarefaction. Number 10, you need to look at the figure again. And what does the red line represent? A, compression, B, rarefaction, C, wavelength, and D, amplitude. Again, what does the red line represent? A, compression, B, rarefaction, C, wavelength, and D, amplitude. Last time we defined what a wave is. We learned that it is a disturbance moving away from a source and carrying energy with it. I demonstrated it using water ripples in a basin. The source of disturbance is the coin I dropped onto the water surface, and the dropping motion transfers energy to the water, which then carries that energy through water ripples going to the walls of the basin. We also talked about two important characteristics of a wave. We have number 1, amplitude, which is the maximum displacement from the resting position to the top of a crest or to the bottom of a trough. And number 2, wavelength, which is the distance between two successive crests or two successive troughs, and which is also equal to the distance between any two identical points on successive waves. Finally, we looked into the waves as carriers of energy, which we will expound more in this lesson. In our example of me playing the guitar, we say that the amplitude of a wave is directly proportional to the energy associated with the wave. Moreover, in our example of red light versus blue light, we say that the wavelength of a wave is inversely proportional to the energy associated with the wave. Now that we have a pretty good understanding of amplitude and wavelength, I want to introduce you to another very important characteristic of a wave, which is frequency. According to our definition, frequency, F, is the number of waves that pass a point in a given amount of time, and it is usually measured in hertz, right? We can think of frequency as how often a wave passes a fixed point, alright? But how do we measure the frequency? It's simple, and an easy way to do this is to count the number of crests of waves that pass a fixed point in 1 second. Again, to do this, we need to count the number of crests of waves that pass a fixed point in 1 second. To understand it better, let's have some mathematics to expand our understanding. If we have 20 hertz, then there are 20 cycles per 1 second. We can think of it as if there are 20 crests that passed through this fixed red line in 1 second. Therefore, this person here needs to wiggle his or her hands very fast so that in only 1 second, he or she can make 20 crests pass through this red line. Alright? Now, if we have 300 hertz, then there are 300 cycles per 1 second. We can think of it as if there are 300 crests or 300 troughs, whichever you like, that pass through this fixed point in only 1 second. Therefore, this person here needs to wiggle his or her hands very, very, very fast so that in only 1 second, he or she can make 300 crests pass through this red line. Now, to check our understanding, let's have this question. Suppose a wave has a frequency of 950 Hz. How many cycles does this wave produce in 1 second? Again, we can think of it as if there are 950 crests or 950 troughs that pass through a fixed point in 1 second. Do you have your answers? Great. The answer is 950 cycles. Correct. We also have to remember one of the most important relationships that is between frequency and wavelength. It states that frequency is inversely proportional to wavelength. Again, it is inversely proportional to wavelength. So the relationship is inversely proportional. This simply means that if we increase the frequency, we decrease the wavelength. And the opposite is also true. If we decrease the frequency, we increase the wavelength. As you can see on the screen, we have here an illustration of a wave which is familiar to you since you encountered this in the previous lesson. Now, let us compare red and violet. Which do you think has a longer wavelength? Is it the red wave or the violet wave? As we can see, the red wave has a longer wavelength, right? Now, since the red wave has a longer wavelength and the violet wave has a shorter wavelength, then red has lower frequency while violet has higher frequency. Right? Again, as we can see, the red wave has a longer wavelength and the violet wave has a shorter wavelength. Therefore, red has lower frequency while violet has higher frequency. Again, I want you to remember the relationship inversely proportional. If frequency increases, then wavelength decreases. And if frequency decreases, then wavelength increases. Alright, now let's check your understanding. Which of the following has higher frequency? Now, to know which one has higher frequency, let us first check the wavelength. Okay, that's the first step that we need to do. Between A and B, which has longer wavelength and which has shorter wavelength? As we can see, A has a longer wavelength, right? While B has a shorter wavelength. Now, we know that the relationship of frequency and wavelength is inversely proportional, which means that when wavelength increases, frequency decreases. Alright? And where wavelength decreases, frequency increases. So between the two, we can see that A has a longer wavelength, so it should have lower frequency. Right? While B, having shorter wavelength, has higher frequency. Right? Students, I want you to remember that in letter A, longer is associated with lower. Right? Just remember two letter L's. L for longer and another L for lower. This that I will show you next will be our ultimate guide in our following discussion. You can take a screenshot of it or draw it or make a rough sketch on your paper. You can see on your screen a concept map, right? This is called the concept map. As an overview, waves can be classified as electromagnetic or mechanical. Electromagnetic waves are always transverse waves, while mechanical waves can either be longitudinal or transverse waves. Later on, we will digest this concept map. I will also share demonstrations of how these are different from each other. Okay? Again, when reading a concept map, we just need to follow the arrows, alright? And those words that are contained inside the boxes. Again, waves can be classified as electromagnetic or mechanical. Electromagnetic waves are always transverse waves, while mechanical waves can either be longitudinal or transverse waves. Alright? Let's begin with mechanical waves. Mechanical waves are caused by a disturbance or vibration in matter. Can you recall what matter is? Matter includes solid, liquid, and gas. We also have what we call plasma, but for now it's enough for us to understand that matter includes solid, liquid, and gas. And when we are talking about waves, we call that matter as medium. Alright? We change the word matter into medium when you're talking about waves. Alright? For example, waves in water are formed because of the vibrations in the liquid medium. Right? We cannot create water waves without water. What I just mean to say is that for mechanical waves like water waves to be created or be transferred from place to place, there should always be a medium, which in this case is water. Another example is sound waves. We hear sounds because there are sound waves that are being delivered from a source to our ears. And that sound cannot be delivered without a medium, which in this case is air. Alright class, so what I have here is a wooden shaker. It is a kind of instrument. And when I shake this shaker, you can hear the sound coming from this wooden shaker. This is the source of the sound wave. And the sound waves coming from this source travel through the air going to your ears so that you can hear, you can process the sound. Alright, now the molecules in the air are kind of vibrating when the sound wave passes through those air molecules, and it reaches to your ear and you can hear the sound. Alright, now without air, you cannot hear the sound. Okay, again, air is a gas, and gas, we know it is a phase of matter. So therefore, if there is no air, you cannot hear the sound of this wooden shaker when I do this motion of shaking. Right? This is because, again, when we are talking about mechanical waves travel through a medium, and air is a phase of gas, and gas is a matter, and when we're talking about waves, we refer to matter as medium. Right? So essentially, you cannot hear anything without air. Now, let us have electromagnetic waves. Electromagnetic waves are waves that do not require a medium to propagate. It is crucial to understand that mechanical waves require a medium, but electromagnetic waves do not require a medium. Right? It means to say that electromagnetic waves, or EM waves for short, can travel with or without solid, liquid, gas, or plasma. It can actually travel through a vacuum. When we say vacuum, there are no molecules in there. It is an empty space, a region of space with no matter, no solid, no liquid, no gas, or no plasma. And as we can see on the slide, we have stars, right? I use this image because the outer space is almost a vacuum. Now, do you think electromagnetic waves can travel through outer space? We'll get back to this later. For us to have a good overview of electromagnetic waves, let us look at the electromagnetic spectrum. We will not really delve into this right now, but we will discuss it elaborately in the next lesson. What you can see is a picture of waves with different ranges of wavelengths. Right? Starting from the left, we have radio waves, microwave, infrared, visible, ultraviolet, X-ray, and gamma ray. Again, starting from the left, we have radio waves, microwave, infrared, visible, ultraviolet, X-ray, and gamma ray. An example of radio waves is the one transmitted when we listen to a radio. Microwaves are the ones that we use in our microwave oven. For infrared waves, when you go camping with your friends overnight and you build a fire, you experience infrared energy coming from the fire. Right? That's why you feel the heat coming from the fire. Now, visible lights are the ones that allow us to see. We cannot see anything without it. An example of ultraviolet rays is a small portion of the light that is produced by our sun. And remember, we need to keep ourselves away from too much exposure from the sun because the ultraviolet rays can be harmful for us. And for X-ray, an example of it is when we see a doctor and the doctor wants us to have a chest X-ray, just like what you can see in the picture. An example of gamma rays is the one which is produced by the hottest or yung pinakamainit na object in our universe. Like when a star explodes or sumabog. And these are all examples of electromagnetic radiation. Meaning, all of these can travel in electromagnetic waves. And I mentioned electromagnetic radiation, right? Which is commonly known as light. Again, electromagnetic radiation is also called light. Therefore, all the examples I mentioned, from radio waves to gamma rays, are all examples of light. Anyway, we will talk about it more when we discuss electromagnetic waves in the next lesson. We know that what gives us light is the sun, right? The light that's coming from the sun travels for about 8 minutes to reach our planet. Question: through what does light travel? Does this light travel, the light coming from the sun? The answer is it travels through the outer space. And interestingly, outer space is almost an absolute vacuum, which means that there is almost no atom, no molecule, no compound present in there. Did you get it? The light coming from the sun travels through a nearly vacuum region in the outer space before reaching the Earth. Now, can we say that light can be described as an electromagnetic wave? A big yes for that. Why? Because light can travel through an empty space. Light can travel without matter. Light can travel without a medium. Therefore, light is an electromagnetic wave. It can travel as electromagnetic waves. Just a quick recap of what we already know. We discussed the differences between mechanical and electromagnetic waves. Mechanical waves require a medium for it to propagate or travel. Meanwhile, electromagnetic waves do not require a medium to propagate. Now, let us have the next part of our lesson, which is the differences between transverse and longitudinal waves. Are you ready, class? Great. I am again showing the concept map that we used a while ago. As you can see, mechanical waves can be transverse or longitudinal waves. Let us look at the differences. In transverse waves, the movement of particles is perpendicular to the motion of energy. Now, can you still recall what perpendicular means? I will help you remember. I'll show you a question. Which of the following lines are perpendicular? Which of the following lines are perpendicular? If your answer is D, then you are correct. I am grateful that you still remember what it means. When we say that two lines are perpendicular, then they are related at a right angle. Alright? What does it mean when we say right angle? It is 90 degrees. In letter A, one line is straight, but the other is somewhat slanted, and it looks like a greater than sign. Right? In letter B, two lines are straight relative to each other. In letter C, one line is straight, but the other one is somewhat slanted, and it looks like a less than sign. But in letter D, the angle that lines created is 90 degrees, which is what we call a right angle. And this is true for transverse waves. The movement of the particles and the motion of energy are related by 90 degrees. So if this line represents the motion of energy, then this line represents the movement of the particles. Class, I want you to take a look at this graph. This is called an XY graph. We have an x-axis and the y-axis because we will use this later. Alright? This is a familiar figure, right? We have here the simplest representation of a wave. Just to have a recall, these are the crests, these are troughs, these are amplitudes and wavelengths. Now let me put this figure on a graph. The x-axis shows us the direction of the energy. Alright? While the y-axis shows us the displacement of the particles in motion. Again, the x-axis is the horizontal line while the y-axis is the vertical line. Alright? Can you tell me what is the direction of the energy transport? Just look at the word energy. Okay, just search for it and then determine the arrowhead's direction. Is it to the top, to the bottom, to the left, or to the right? Okay, just look at the x-axis and look at the arrowhead. And if your answer is to the right, then that is correct. Great job, student. Now, how about the direction of particles? Just look at the word particle. Just search for it and you will know the answer. If we will see, the y-axis is the displacement of the particles in motion, which essentially is up and down, right? Can you follow? Good. So the movement of particles is vertical up and down. Alright? And this movement is perpendicular to the direction of the energy transport. You can imagine this form of wave as sea waves. That is why I colored it blue. This wave is going in one direction, which is to the right. And we can think of it as the seashore. And if you're on a swimming float, still enjoying the sea, You will feel that you are moving up and down and up and down when the wave passes through you. Do you have such an experience? Perfect. Now let's proceed to the next. In longitudinal waves, the movement of particles is parallel to the motion of energy. Can you still remember what parallel means? Let me show you this question similar to what I showed you earlier. Which of the following lines are parallel? If your answer is B, then great job, correct. When we say that two lines are parallel, then the two lines are not touching each other at any point, even if we extend this line so long, like infinitely, never ending. So in letter B, the line above is drawn perfectly horizontal, and the line below is also drawn perfectly horizontal. Let's check the other choices. In letter A, the lines form something like a greater than sign. In letter C, the lines form something like a less than sign. And in letter D, the lines are perpendicular. Going back to letter B, if the movement of particles is represented by this line, then the motion of particles is represented by this line. Can you follow? Great. In the following discussion, I want you to focus on the figures that I'll be showing you. Is that good? Excellent. This one is an undisturbed medium. What do we mean by undisturbed medium? This means that there is no wave that travels through or propagates in this medium, which can be solid, liquid, or gas, or plasma. Now, the next figure is now disturbed. There is a disturbance which causes waves traveling through this medium. This is a common representation of longitudinal waves. However, this is quite different from the figure I showed you when we discussed transverse waves. Hence, it will be good for us to first define the parts of a longitudinal waves. Okay? This where the particles or lines are very close to each other are what we call compressions. From the word itself, the particles are being compressed, packed closely to each other. Okay? This one, where the particles or lines are farther apart, is what we call a rarefaction. Now, the distance between two consecutive rarefactions or the distance between two consecutive compressions is the wavelength. We usually measure the wavelength between two consecutive compressions because it is way easier. Right? Going back to the figure, let me show you what I mean by parallel. What I have here is a slinky, right? I attached the other end here and I am holding the other end. And let me just arrange my camera. If I push it a little bit, it would create this kind of pulse that runs from my hand going to that direction where I attach the other end. Right? Let me just repeat it. You can see parts of the slinky or a part of the slinky where there are circles or there are parts that are compressed. Okay? And this is what we call compression. Now, the direction of the pulse or the direction of the compression we just created is going to that direction. This is to the right direction. Let me show you again the compression. Later, I will show you a picture so that we can clearly see what's going on here. Right? Now, how about the direction of the energy transfer? It is going to, yes, it is going to the right because I aimed the motion through pushing the slinky a bit, going to that direction as well. And also, one of the manifestations of the direction of energy is the compression, which we saw traveling near my hands, going to the other end. Again, we're doing some pushing, and you can see there were parts that were compacted or close together. This is what we call compression. And since I aimed the pushing to that direction, then the direction of the energy transfer is to that direction also. Now, this figure that I am showing you gives you a clearer picture of what the slinky toy looks like when I do some pushing and pulling. The green arrow points at the direction of the energy transfer, and the orange arrow points at the direction of the particle motion. Are they parallel or perpendicular? They are, yes, parallel. Alright? I hope I made everything clear, class. And just to have a quick recap, we learned the differences about transverse and longitudinal waves. In transverse waves, I just want you to remember perpendicular. This is because the direction of the energy of the wave is perpendicular to the particle motion. Meanwhile, in longitudinal waves, I just want you to remember parallel. This is because the direction of the energy of wave is parallel to the particle motion. Now, for the third time, I will show you the concept map. But this time, I want you to follow me in saying the relationship among the concepts inside the boxes. Alright? Alright, let's start. Waves can be classified as electromagnetic. Electromagnetic waves are always transverse waves. Waves can be classified as mechanical waves. Mechanical waves can be classified as transverse waves. And also mechanical waves can be classified as longitudinal waves. And for the sake of practice, let's repeat. Waves can be classified as electromagnetic waves. Electromagnetic waves are always transverse waves. Waves can also be classified as mechanical waves, and mechanical waves can be classified as transverse waves and longitudinal waves. I hope that everything is clear now, class, and let us go back to the set of questions we had in the first part of the lesson. Are we now ready to answer those? Alright, number 1. What do you think is the answer? It is letter C. Alright, we learned in the first part of our lesson that frequency is the number of waves that pass a point in a given amount of time, which we usually measure in hertz. Number 2, which do you think is the correct answer? It is letter B. Frequency is inversely proportional to wavelength. And we show in our lecture that as frequency increases, the wavelength decreases. And as frequency decreases, the wavelength increases. The relationship is inversely proportional. Alright? Number 3, based on the choices, one can be segregated because it is not a medium. It is not a matter. It is not a solid, not a liquid, not a gas, or not plasma. And what do you think is the answer? It is letter C. A narrowlog is solid, cooking oil is liquid, and helium is a gas. However, a perfect vacuum means that there is no single molecule or atom which we know makes up matter. So only C is not a medium, and mechanical waves cannot travel without a medium. And notice that I did not put anything under letter C because vacuum is literally nothing, right? Number 4. Do you have your answer? It is letter C. Light coming from distant stars. We know that choices A and B are both sound waves, which are mechanical waves. We also know that jumping rope is an example of a medium through which mechanical waves travel. Yet, the light that comes from distant stars is itself light. Alright, going back to this slide, we learned that when the star bursts, it emits gamma rays. And gamma rays are forms of light. And we know that light is an electromagnetic wave. Alright? Next, number 5. Is it true or false? The answer is false because electromagnetic waves do not require a medium to propagate. It can actually travel without it, just like in outer space, although it is not perfectly a vacuum. Again, a vacuum is an empty space devoid of matter, and electromagnetic waves can travel through it. Alright? Number 6, true or false again? Let me just repeat. Light travels as electromagnetic waves, and electromagnetic waves travel as transverse waves. So it should be true. Alright? Let me go back to our concept map. Again, light is an example of electromagnetic waves, right? And as we can see, EM waves or electromagnetic waves are always transverse waves. Again, the answer should be true. And number 7, We know from our discussion in longitudinal waves, the direction of the particle motion is, yes, it is letter A, parallel to the direction of the energy of the wave. As an example, I demonstrated this using a slinky, right? Just like in our image here. Number 8, we discussed that in transverse waves, the direction of the particle motion is blank. It is letter B, yes, perpendicular to the direction of the energy of the wave. And as an example, we recalled our experience on a beach when when a wave came rushing through the shore. Second to the last, based on the anatomy of the longitudinal wave, the arrow is pointing at a compression. Okay, we know that it is a compression because the particles are very much closer to each other. And lastly, the red line represents a wavelength, right? So the answer should be wavelength because it shows us the distance between two compressions, right? Did you get all the answers correctly? Fantastic. Let us know it in the comment section. If you did not get all the answers correctly, that's okay. Maybe you should have a practice. And later, I will show you a couple of assessment activities which I am sure will be helpful for you. Again, in this lesson, we started with another important wave property, which is frequency. Our main focus, however, was the differences between mechanical and electromagnetic waves. Mechanical waves require a medium to propagate, while electromagnetic waves do not require a medium to propagate. And also we focus on the differences between transverse and longitudinal waves. In transverse waves, the direction of the movement of the particles and the direction of the energy are perpendicular to each other. Meanwhile, in longitudinal waves, the direction of the movement of particles and the direction of energy are parallel to each other. Alright, that would be all for our lesson about the differences between a mechanical wave and an electromagnetic wave, and the differences between transverse waves and longitudinal waves. I hope that I made it clear to you, and let's continue to enjoy learning because science brings a lot of fun. I believe that practice makes a habit, so you can check our website, PhilSciHubEd, and there's a link for your assessment activities. We have a wavy topsy-turvy for the wave ang person, a compare wave study, waverish, guess the gibberish, free, queen C, and waves flow in you. Of course, don't forget to visit and message us on our social media accounts, www.philscihub.com, at PhilSciHub on Facebook, PhilSciHub TV on YouTube, and at PhilSciHub on Twitter, Instagram, and TikTok. Here are the references that I used, and we also appreciate it if you comment on our video lectures by answering the Google form link that you can see on your screen. Thanks so much for watching, and I know that we all learned from this lesson. Again, I am Kerby, one of your Filipino Science Hub teachers, and I am glad to help you learn.